Hello everyone, welcome back. Good evening. Welcome for the next session on Algebra. All right, so today we'll be looking at quadratic equations and polynomials of higher degree. Right, let's start with this session. Right, again, have brought quite interesting problems for you to look at. Right, along with some previous year questions. Right, uh, so right, we have already gone through linear equations, um, and today quadratic, so second order polynomials, and some problems will also take of higher degree polynomials. We'll have two sessions on this topic today as well as the next one, right? So let's see what we have. First question in front of all of us. Here we go. If p and q are positive integers such that 2p square 15 into bracket 2p square minus q square is 7pq, so a quadratic kind of expression we have, but involving two variables p and q, not just one, then a possible value of 3p plus 2q is what from the options. So obviously there is nothing that we can solve without the options. Basically the question is asking of the possibility. Now this question primarily rests on the fundamental constraint given in the very first phrase: p and q are positive integers, right? So my focus is that I'm able to tell you that CAD is focusing a lot these days on asking questions with this constraint that my variables are integers, and then he asks something. So that's the style of this problem. All right, so it is that constraint which binds the problem through which the logic emerges. So p and q are integers, and then this equation is there, and then we have to find the possible value of this expression 3 into p plus 2 into q. Let's work first of all with what we are given. Let's simplify that. We have been given, simplify this, expand everything in. So we have 30p square, right? Take 7pq over here, so that it looks like a quadratic expression. Minus 7pq minus 15q square is 0. That is what we have. Now as we always do with any quadratic, we split the middle term, right? So 30 into 15 is the product of the extremes. So we should try to break the middle term 7 such that the difference of the two factors of 13 15 is 7, right? Okay, so 13 into 15 is basically 450. So how can we express 450 as the product of two numbers which differ by 7, right? Okay, uh, so let's keep on thinking on that. We have 450, it is 45 into 10, but we need numbers to be little closer together. It is also as good as, can I say 20, 450 to 25, it is divisible by 25, and it's 25 into 18. Yes, exactly, that is what we're looking for. So now we have split the middle term as 25 and 18. So we have therefore that 30p square minus 25pq plus 18pq minus 15q square is 0. Then we should be able to get something over here, 5p and bracket 6p minus 5q, and from here we'll have 3q, and again as we are expecting the same thing will come 6p minus 5q, right? So it gets factorized as 5p plus 3q, 6p minus 5q 0. Now since p and q are positive integers, so 5p plus 3q can never be 0, because if that is the case, then it definitely means that the two quantities are of opposite signs. One of them is positive, other is negative. So this is not possible. This is ruled out. So only this is possible. So 6p should equal 5q because of 6p minus 5q 0, or p is to q is 5 is to 6, because p by q is 5 by 6, right? The ratio we have obtained. So this is the simplest ratio of these two numbers which are integers. So that is the whole point, and therefore what we can say, p must be a multiple of 5, q must be a multiple of 6. So that is the logic that emerges, and hence we can now attack the problem. So what's my 3p plus 2q, right? So taking these parameters, I can say 3p means 3 into 5, so 15k, and 2 into 6, so 18k. Sorry, 2 into 6, 12k, sorry, 15 and 12. So this is coming to be 27k. So therefore, I am able to understand it must be a multiple of 27. So therefore, my option C becomes correct, right? 81 is possible. Others are not. So how we started from a quadratic and then we factorized it. Then we came to the core idea of the problem. We are dealing with integers. So therefore, we got them in a certain ratio and then we deduced the possible value of the given expression, right? Okay, so that was this one. Now, coming to the next one, it's a core question on quadratics. Let alpha beta denote the roots of the equation x square minus 6x plus 4 is 0. What is the minimum possible value of the function fx is x minus alpha whole square plus x minus beta whole square? In any quadratic, if we are given the actual coefficients and everything, the first thing that we can always identify is that alpha plus beta and alpha beta means sum of roots and product of roots, right? Ax square plus bx plus c. So alpha plus beta is minus b by a and alpha into beta is c by a. So that's what we can write from here. And then once we write that, then we can start to think about minimization of this quadratic function, right? So first of all, my alpha plus beta over here is 6, right? And alpha into beta is 4 for the given quadratic. Now, based on that, let's come to define my fx, right? I think I have to simplify this quadratic by knowing this data about the roots and then putting it over here. So the whole point is alpha beta are basically irrational numbers. That is very clear, right? This quadratic does not have a factorization in the integer form. So the roots are irrational. So it is very tedious to actually put over here the actual numerical value of alpha and beta. So we have to just make use of the alpha and beta from here, the data about it, and then use it over here. So expanding this, what will this give me? So can I say I'll get x square plus x square 2x square minus 2 alpha x from here minus 2 beta x from here. So that is minus 2 alpha plus beta x. I'm just combining the whole perfect squares added up, taken together, right? X square minus 2 alpha x minus 2 beta x and plus alpha square plus beta square. Now that alpha square plus beta square, I want to be able to write in terms of this data. So can I write alpha square plus beta square as alpha plus beta whole square minus 2 alpha beta from my simple factor expansion rule? Now, therefore, everything I have written in terms of alpha plus beta and alpha into beta. Now I can put in my numbers, right? So therefore, this quadratic function, right, fx gets simplified as 2x square and alpha plus beta is 6. So 6 into 2, 12x plus alpha plus beta whole square. So 36 minus 2 into 4, 8. 36 minus 8, which is 28, right? 2x square minus 12x plus 28. Now I have to minimize this quadratic add. That's the last thing. So that we can always do by the process of completion of squares, right? We complete the squares and then we are able to minimize. So first of all, take 2 common. We have x square minus 6x. If I write x square minus 6x plus what will make it a perfect square? So this is the expansion of x minus 3 whole square, x square minus 6x plus 9. And then this is 9 into 2, 18, but this was 28. So what is remaining? 10. So this is a perfect square plus 10. So minimize for the minimization purpose, we will put the perfect square to be 0, right? The minimum value of a perfect square is 0. A perfect square is non-negative. So therefore the minimum value is coming to be 10 because that is the remaining number left away, right? Yes, perfect, Avinash. Okay, I'll give you the next problem and I'll give you some time to think now on the next one. I'll just read the problem for you. For how many integer values of k the function fx equals this? So it's a quadratic function with k as a variable over there, is strictly positive for all values of x. All right, let's try this, everyone. Let me see if somebody can get this. I'm looking on your comments. All right, let me start discussing and let me know if you're getting it right. Okay, so when is a quadratic function going to be strictly positive? What does it mean to be strictly positive? Means basically, if you plot the function, it is never touching the x-axis or going below it. It is always staying above the x-axis, right? Effectively meaning that the quadratic function does not have any roots. Which for which what is the condition? The condition for no roots, discriminant is negative. So effectively all this implies my discriminant is negative, so that it is strictly positive, so that the graph looks something like this, right? Not touching or going below the x-axis, always staying above it. No roots, discriminant less than 0. So that is the condition that we have to apply, discriminant less than 0, and that will give us the possibilities of k, right? So let's put this condition. D, what is discriminant? D is discriminant is b square minus 4ac. So put that. So therefore b, which is this minus 2 into 4k minus 1 whole square. So that will become 4 into 4k minus 1 whole square minus 4 into 1 into this thing. So this is 15k square minus 2k minus 7. This needs to be less than 0. Since this is less than 0, I'm solving an inequality. So this 4 I can cancel off. So I'm just expanding this and this, right? So 4k minus 1 whole square becomes 16k square minus 8k plus 1. And minus of this thing in bracket, 4 I have just cancelled off, right? So minus 15k square plus 2k plus 7 is less than 0. So 16 minus 15, which is only k square, minus 8k plus 2k, so minus 6k, and 1 and 7, 8 is less than 0. Right? So I think this has a very easy factorization. K minus 2 into k minus 4, right? 8 is 2 into 4 and 2 plus 4 is 6. So k minus 2, k minus 4 is less than 0. So this now this quadratic inequality, right, is there. K minus 2, k minus 4 looks like this. It has roots 2 and 4. So it is negative between 2 and 4. So this is the solution range. But since k, we are looking for integer values of k. So how many integers are there between 2 and 4? That is the answer. Only one, right? So the only integer value of k which satisfies this inequality is only one value, which is k equal to 3. So what is the answer? The function is strictly positive for only one integer values of k, right? So quite a I think in complete logic of quadratic, I think, has been used in this problem. All right. Okay. Next one. Let fx equal to ax squared plus bx plus c be a quadratic such that the roots alpha and beta satisfy. So we have some condition given over here. Alpha plus by 1 by beta equals beta plus 1 by alpha, and also alpha should not be equal to beta. Then which of the following is necessarily true? So basically there is a condition on the roots about a general quadratic function, and then we have to derive that what kind of condition must be there with regards to the coefficients of the quadratic. All right. So let's, so obviously we have to work on this. Let's simplify this. Let's bring all the terms on one side first. Alpha minus beta plus 1 by beta minus 1 by alpha. Right. This is 0. Okay. So alpha minus beta plus alpha beta here, and alpha minus beta is 0. Right. Okay. So alpha minus beta looks to be common from here. So I can say that alpha minus beta times 1 plus 1 over alpha into beta is 0. Now comes into picture this condition that alpha is not the same as beta. So if alpha is not the same as beta, which means that this is not 0. So for this product to be 0, this term should be 0. So 1 plus 1 by alpha into beta should be 0, which is as good as that alpha into beta plus 1 is 0, right? Because on taking the LCM, and obviously denominator can't be 0, so numerator must be 0. And therefore what we finally get, alpha into beta is minus 1. This is the final result that we get on simplifying. So if alpha into beta is minus 1, so what is minus 1? C by A is minus 1. That is the value of alpha into beta. The product of roots is C by A, means C equals minus A, means C plus A is 0. That is here, right? So just follow what was given, simplify that, get the conclusion from that, and then we are able to deduce the required result, right? So that is what algebra, is all about. Just follow the given story of the problem. Okay, now I promise you that this is quadratic equations and polynomials. So now you can see something which is beyond a quadratic. X power 4 is there, so a fourth degree polynomial equation is there, and it is given that alpha beta gamma delta are its roots. Then we have to find the value of this expression, 1 minus alpha, 1 minus beta, 1 minus gamma, 1 minus delta. Now to do this one, we need to be very clear with the concept of um, higher order polynomials and their roots, and the factorization concept. Okay, so the thing that first of all we that strikes us is the symmetry by the symmetric way in which this expression is written, right? 1 minus the root and the product of all such things. Now it is very difficult, or I mean, to actually, so for example, over here we do know what is the value of alpha. I mean, it's the sum of the roots, the sum of the, like alpha plus beta plus gamma plus delta, alpha into beta plus beta into gamma, all that we can find. Means sum of the roots is 9, sum of the product of roots taken 2 at a time is minus 3. All that is there, but there is some other alternate approach required for this particular problem. So if there is any polynomial of n degree, and it looks like in general a naught xn plus a1 x power n minus 1 and so on, until the constant term, let's say last will be a n minus 1 into x plus a n. This whole expansion of nth degree polynomial. So if it has, let's say, root which is x1, x2, x3, then we all know that this equates as a naught, obviously being the first coefficient, will be outside, into the product of the all the factorized terms, which is x minus x1, x minus x2, x minus x3, and so on until the last root. Right. So that's the whole uh, relation which helps us to attack this particular problem. Says that if alpha, beta, gamma, delta are the roots of this fourth degree polynomial, then this expression should be equivalent to x minus alpha, x minus beta, x minus gamma, x minus delta. It should be equivalent to that. So now you can see that this expression can be easily obtained by just inserting x equal to 1 in this. Right? And you already know that it is equal to this fourth degree polynomial. So therefore, this required expression becomes equal to the value of this polynomial at x equal to 1. Putting x equal to 1, therefore we get the answer. So therefore the required expression we are able to get as 1 power 4 1 minus 9 into 1 cube minus 3 into 1 square minus 3 plus 16 into 1 16 minus 1, which is 1 minus 9 minus 8 minus 3 minus 11 plus 16 5 minus 1 4. Right. So so this question just required our knowledge of the fact that any polynomial can always be expressed as the product of all the factorized terms corresponding to its roots. All right. Now I'll take some previous year problems. I have selected some very good questions from the last year problems. Let's see. Okay. So here is this CAT 21 problem. Consider the pair of equations. So we can see that we have been given two equations over here with regards to two variables x and y. So these are not looking like proper quadratic equations as such to solve, because neither can they be factorized the way they are written, and they involve both the variables taken together. X and y both are present in the same quadratic. So although we had the similar expression in the first problem, but there it got factorized because it was of the form like x square and plus something into xy plus something into y square. But this last term is not written in that form that we can factorize this given term. So something else is required over here. If x is more than y, then x minus y equals. So it looks really difficult that we might be able to find the value of both x and y from these equations. It might be possible, but I think quite time consuming. So always such questions have some kind of trick in them. Typically manipulation of the equations is required, and you should just focus on what we are solving for. We are not solving for the individual values of x and y, but only to find the value of x minus y. So how can we come to x minus y? You see in that in this equations, there is x square, there is y square, there is minus xy. X square y square minus xy, so that reminds me of x minus y whole square can be obtained by just taking these both equations and adding them up. Right. So that's the simple manipulation that is required, so that x minus y whole square will come, and then maybe we can find uh, the required value. Right. So adding the two equations, what do we get? X square plus y square and minus xy minus 2xy. So a perfect completion of square happens over here. And then we have obviously minus x plus y also. And that equals 56, 22 and 34. So therefore this becomes x minus y whole square, this much. And since I want to write in form of x minus y, so this is negative of x minus y. equals 56. So now everything is in terms of x minus y only. If I just write a as x minus y, so this is just a quadratic equation in terms of a square minus a is 56, which is that a into a minus 1 is 56. 56 needs to be written as the product of two consecutive natural numbers a and a minus 1. 56 is 8 into 7. A is therefore 8. That's the answer, right? So until unless we think of or visualize this kind of manipulation, it will just go keep on going round and round. So therefore, that simple technique of what you should have thought of, okay, what can we do the equations, adding them, subtracting them. If you had subtracted, you would not have been able to find a suitable simplification. Addition is what is required, right? Algebra is all about manipulations. Little bit hit and trial is also sometimes required, right? So subtraction, if you had done, you would have not been able to reach to the result as required, but addition, you are able to reach there. Perfect. Cat 23, uh, a very good question, this one. Let's see. Let alpha and beta be the two distinct roots of the equation 2x square minus 6x plus k is 0, such that alpha plus beta and alpha into beta are the distinct roots of the equation x square plus bx plus p is 0. So first there is a quadratic, its roots are given alpha and beta. Then there is another quadratic, and then its roots are in terms of the roots of the previous equation, such that the roots of the second equation are the sum and the product of the roots of the first equation. Very nice. And there are some coefficients p and k in variable form, which we have to find, I guess, and find the value of 8 into k minus p. It's a theta question, right? We have to type in the answer. So let's jump in. Obviously, we'll just start writing what we can do about alpha and beta. We can, from this, we can write the sum of the roots and product of roots. Although it will be in variable form, at least alpha plus beta is constant. It is minus of minus 6 by 2. It is 3, right? Minus b by, and alpha into beta c by, so k by 2. So let it be in variable form. We have to simplify it and solve for that. Now for the second quadratic, we know its roots are these two expressions, right? Alpha plus beta and alpha beta are the roots of this, means 3 and k by 2 are the roots of this. So since we have to solve for k and p, now we should just write the equation in terms of the fact that these expressions are the forming the roots of this equation, right? That's the way to go. So we have just got rid of our alpha and beta expression. So the sum of the roots, which is 3 plus k by 2, should equal minus b by, which is minus p over here. And the other equation we can write is that product, so 3 into k by 2, so 3 by 2 of k is p. Perfect. Okay, so this is minus p, this is p, so just equate them with the minus sign. So I'm just writing 3 plus k by 2 is minus p, means minus of 3k by 2, right? Which basically means this comes over here. So this is half, minus 3 by 2 is minus 2k. So minus 2k is 3. So we get that k is minus 3 by 2. And if k is minus 3 by 2, then p was 3 by 2 times of k. So 3 by 2 times of minus 3 by 2, which is minus of 9 by 4. K is minus 3 by 2, p is minus 9 by 4. I think what we have now. So k minus p becomes k is minus 3 by 2 minus p, means minus of minus plus 9 by 4. 9 by 4 minus 3 by 2 is minus 6 plus 9 by 4 is 3 by 4. K minus p is 3 by 4. So 8 times of that becomes 8 into 3 by 4, which is 6. That's the answer. Right. So ultimately, when done, it looks quite doable, right? That is what algebra is all about. Not getting scared with this. the variables. Just jump into the problem, just understand what it is saying, just apply the things, right? Sometimes it's manipulations, sometimes it's jugaad. Okay, let's see. Last problem for the day, for the session. A very conceptual question over here. Let a, b, c be non-zero real numbers such that b square is less than 4ac and fx equals ax square plus bx plus c. If the set S consists of all integers m such that fm is less than 0, then set S must necessarily be what kind of set from the options, right? Perfect. Very nice conceptual problem, right? Nothing to solve here in terms of some variables, but analyze. B square less than 4ac means discriminant is negative. D equal to b square minus 4ac. The discriminant is negative. For the given quadratic, the usual quadratic expression is there. Discriminant is negative means the roots don't exist. There are no roots. Now, the set consists of all integers m such that f of m is negative. Then what is the set S? Means I'm looking to find what could be all the values of the input variable in the function such that the output is a negative one. Let's analyze this little bit from the perspective of how the graph looks like. A quadratic function which does not have any roots, how will that look like? We know that the given condition is discriminant is negative. So therefore we know that there are no real roots. So there are no roots for the equation for the quadratic function. Now, we know that the graph of the quadratic function depends on the sign of the leading coefficient a. If a is positive, it's an upward parabola. If a is negative, it's a downward parabola. So the graph of the quadratic function depends on the value of a. So if I'm drawing the graph, there are two types of the graph. With d being negative, and with a being positive, the graph of this quadratic, which has no roots, will look like this, an upward parabola, right? And going above the x-axis, not touching it, not going below the x-axis. Or else, if d is negative, and if a is also negative, then it's a quadratic which is below the x-axis completely, right? No roots, right? So these are the two kind of graphs. So what could be the set of all the integers m such that f of m is negative? In this case, there is no value of m that exists. In the first graph, the function is never negative. So what would you say about the set S of all integers m? The empty set. It does not exist. The set of all the integers m, they don't exist. There is no such integer m, right? But in the second case, the function is completely negative, always negative. So what is the set m? It is the set of all the possibilities that can be there, right? All the integers. So the set m is either empty or just completely the set of all integers, and that is what we're looking for, right? That is what we had to analyze. So so with this problem, I just wanted to bring in the light that how problems in algebra are also highly conceptual, and your theoretical knowledge of the topic is also sometimes being tested, right? We are not writing a theoretical exam, but theory is also important, right? Okay, so that brings us to the end of today's session, but we'll continue this in the next one. So I hope to see you there. Ask me anything, leave me your comments, right? Your suggestions, your comments. I'm always looking to hear from you, right? So thank you. Thank you so much and see you in the next session. Thank you.